because okay. So let me talk to you about Kelvin waves. We have almost finished. Well, we're basically out of time, so. No, Kelvin Wake. Okay, so anytime an vessel moves through water, we know this wave system it creates, and we've talked about it generates a lot of drag. It's wasted energy. So we can go further and look at the details of this wave system and try to understand how it influences the drag and what we can do to try and minimize this. Of course, you would want to get rid of it completely, but that's impossible. So we have to live with it, and how do we minimize the energy we spend trying to overcome that wave? Okay, so this very specific pattern that we see behind boats, Kelvin realized that, oh, if we have a point particle moving through fluid, theoretically, he showed that you would get similar wave system. Okay, so that's why these are called Kelvin wakes. Now, the most obvious thing about this wake is the lateral waves, right? We see this V-shaped diverging waves moving out. But there's another wave system. You see that better here, all right? So there's these wave crests that become visible. You see in front of the boat, there's no waves at all. It's a calm day. But behind the boat, there are these ridges, okay? So there's these two independent wave trains, one moving backward and one moving sideways, okay? And these two interact with each other. So let me okay, so when we talk about wave system created by a ship, and this wave system is called Kelvin wake. Okay, and Kelvin showed that you will end up getting these two systems, a transverse system of waves and a diverging system of waves. So two main characteristics are you get diverging waves and he showed that the crests of these waves would be inclined at in a given range of angles. So with the crests, their crests. For a long time, people took this 20 degrees, or rather 17 degrees, to be like a law of physics. But now there's a lot of debate about, okay, it's not 17 degrees, it's 15 degrees, or it's 18.5. So yeah, I mean, the number is not exact, but it's roughly 20 degrees. So that's the wave system that moves sideways. And then there's the other. And if we make a sketch of this, let's say this is the direction of motion. And there is our point pressure source that's moving. So it gives out this.
So we're just gonna act like you didn't murder us with that quiz?
What? No, it's for, I mean, you requested it, so you could drop your lowest grade. So
Can you drop my lowest two at this point, man? Come on, man.
no, don't worry. I mean, I mean, yeah, I'll give you partial points for the steps. So yeah, don't worry.
Hey, give us half and then partial points.
All right. Yeah. So you get these multiple waves as the boat or any vessel moves through. So these, the red ones, transverse waves. And the blue ones are the diverging waves. Okay. And the nice thing about these is there's a very specific wavelength for these. And you can predict what the wavelength is.
Can you show the top part of the page for a sec? All right, thank you.
Sure. So what would you say the wavelength depends on? Does it depend on the size of the boat, something else?
I would guess the speed.
Okay, that's correct. But why do you say that?
Well, because the waves are going to be moving sideways at a constant velocity. And the basically the horizontal velocity is going to be determined by your boat speed.
Yeah, so see these, the transverse waves move at the same speed as the boat, okay? And we've learned how to relate the time period, the wavelength, and the speed of the wave, the celerity of the wave in wave mechanics, okay? So if you know the speed of the wave, if you know the water depth, etc., you can predict exactly what the lambda would be. Okay, so let me just do a very quick recap of what we know. The first thing, we observe such wave patterns. If the water is too choppy, then of course there's the waves in the lake itself or the ocean itself that'll interact with these and probably destroy them. But from the pictures we saw, when it's perfectly calm, then these become very, very obvious. And these transverse waves move at the speed of the ship. And when you know that, you can predict that the value lambda is equal to 2 pi v squared over g. This is a V ship or V boat. And to see where this comes from, you remember this equation? Very, very useful equation. Shows up all over the place. So this is the dispersion relation from wave mechanics. Okay, if you remember, this is 2 pi over t. This is 2 pi over lambda. This is the water depth. Time period, wavelength. This is the hyperbolic tangent. Okay, when we rearrange this, what do we get? We get lambda over t squared equal g over 2 pi. Okay, and you remember the celerity or wave speed is lambda over t. So this gives us c squared is g lambda. Okay, do you also remember deep water? What happens to the tanh?
Isn't it just 0 or
One. It's one.
one? I'm sorry.
In shallow, it becomes KH. Okay, so that's the, this is the one we talk about, tanh, right? Okay, so deep water, we get tanh KH goes to 1. And this gives us the c squared equal g lambda over 2 pi. Okay, and if you see, this is exactly what we have here, right?
Can you show the top part of that page? I'm sorry, man.
So celerity of the wave, if you say the wave speed is the same as boat speed, I can replace the c with v shape. Okay, and that's how you get that. Yeah, you'll get these nice wave systems when you're in deep water. Remember, shallow water is really a very restrictive criterion where lambda over h is less than 20. So you'll almost never operate at speed in shallow waters. Yeah, and let me just remark that since c wave is equal to v boat, we get v squared is g lambda over 2 pi. Okay, so you can predict if you know the speed of the boat, you can predict what wavelength waves you will generate behind you. Okay, now let me just show you what happens. So I'll send you this picture so you have it, and so no need to draw anything. What happens when your bow is moving through water is it generates a wave, right? And depending on your speed, that will determine what the wavelength of this wave is, right? So how many wave crests you have. And the stern generates another wave system. So these two different systems will interact with each other, okay? And they can either take away a lot of energy from you, or at certain conditions, they will cancel each other, which saves you energy, okay? So we'll talk about how these conditions affect our total resistance, okay? But for now, if you haven't already done the spot, just please do that. So for grad students, if you don't know, just go to spot.fau.edu. And that's just an evaluation of the class. Spot is not a good place to complain about when the class is offered, because that's just Spot is just you evaluating my teaching, okay? So, but when you get your exit interview with the department chair, that is the perfect place, okay? So, yeah, so for the spot, if you do write comments, please mention how you would change things so it helps you learn the material better. That really helps me adjust the teaching style, okay? So please log on and do this now. Yeah, well, I'll wait until our class time runs out. Some of the grad students, it might not show up for you because there's only like 4 people registered in the class for grad, and there's a minimum requirement of at least 5 students required. So if it doesn't show up, that's fine. And of course, it's completely anonymous, so don't just say nice things. Give an honest feedback because it really helps change the material, what you say. All right, guys. So just whenever you're done, just yeah. Um, I'll see you Friday, and well, I'll see you tomorrow. So good luck for your presentations. Yeah. See you.